All right, welcome back, everybody. Hopefully, you all did well on the first test this week. Um, for the rest of this week, we're going to discuss a really important topic in statistics, which is probability. It's one of my favorite things to discuss, and I think that you'll find some of these topics really interesting. But this week, we're mostly just going to talk about what probability is and how it works in certain situations. In upcoming weeks, we'll relate it back to the statistics concepts that you've been learning over the previous few weeks. And so it's going to seem a little different, but it'll all make sense in the end. And in general, students tend to find probability questions a bit easier because it's something that you somewhat intuitively understand. If I ask you, what is probability? You're likely going to say something like the chance of something happening or the likelihood of something happening. And that's everybody's general definition. Everybody has some idea of what probability is. Okay, but we're going to specify that definition in a couple of particular ways. And I'm going to show you how to use it to actually figure some things out and more in the next section. Probability measures what is the likelihood of possible outcomes for any given type of situation. Okay, in these situations, we call them events. Okay, so if we want to find the probability of some event, right, what we want to do is find the things that we're interested in, right? What do we want to happen, right? What are we expecting to happen? Okay, divided by the total number of outcomes that are possible. Okay, so for example, if we were to flip a coin, right, and we wanted to find the probability of getting heads, well, there's only one way to get heads when you flip a coin out of two possible outcomes. Okay, with 1/2, which is just 0.5, right? 50-50. You guys understand that intuitively. You understand how a coin flip works. In probability, okay, the heads tails part, we call that the sample space. Okay, that is all the possible outcomes, just basically listed out. In a lot of situations, we can write out the sample space. In some situations, we could if we wanted to. It might just take a really long time. Okay, but you want to have a general idea of the sample space before you at least try to answer some of these questions, as you'll see. Okay, and we're going to talk about the next one, which is rolling a fair die. Right? If you have a single die, 6-sided, right, you can roll it, and you can get any number between 1 through 6. And we'll talk about that in the first example. It is very important that you understand that probability can only range between 0 and 1. I often ask my classes, how many values are there between 0 and 1? And if you take just a second and think about it, there is an infinite number of values between 0 and 1, which means we can assign an infinite, there's an infinite amount of ways probability can be assigned essentially to a situation, right? You can have anything can occur between this 0 and 1. Okay, and so that's important to remember because if you accidentally make some mistakes, you might wind up with a probability that's more than 1, right? And that's definitely not correct. Okay, as percentages, they can range from 0% to 100%. That's probably what you're more familiar with. And you can also see them as decimals as well. We can write probabilities as all three. Pay attention to what your ALEKS assignments ask for as to which one, whether they want the percent of the decimals. Okay, if we have a probability of 0, okay, that implies that the event is not going to occur, right? There's no way for it to happen. Okay, it's essentially impossible. Okay, if we have a probability of 1, that says that the event is guaranteed to happen. Okay, it's always going to happen every single time, 100%, no matter what. Almost nothing has a real probability of 0 or 1. I'd often say that everything is, not everything is, or nothing is impossible, right? But some things are just really improbable. There are things that could happen really rarely, but they're probably not going to never happen. Okay? When we write probabilities in statistics or just in math in general, we generally write a capital P. Okay? And in the parentheses, we write either an E or a word that represents or a symbol that represents what it is that we're trying to find the probability of, right? So in this case, this would be the probability of whatever event E happening. That'd be the probability that we're looking for. So let's talk about some examples of this. Here we have the fair die, right? We want to know what the sample space is. Well, that was before, right? We always write a sample space with brackets. Okay? And if you roll a fair die, you've only got 6 options, which is 1 through 6. So let's talk about these other probabilities. The probability of finding an odd number, right? Well, there are 1, 3, and 5. Those are odd numbers. And so the probability of finding an odd number would be 3. There's the 3 events we're looking for, right? Those are the outcomes that we're interested in, divided by the total possibilities, which is 6. Okay? Or if we reduce that as a fraction, 1/2, and again, we can write it as a percent, or I'm sorry, as a decimal and as a percent. So 50% of the time, if you roll a die, you'll get an odd number. That should make sense to you, because that should feel okay. Right, same thing, we want to find the probability of getting a 2. Well, if we're just interested in 2, well, that's only 1 outcome out of the 6. And we can't reduce 1/6 any, but we can write this as, I believe it's 0.167. Let me check that real quick. That is right. Okay, or about 16.7%. Now, what if we wanted to find the probability of rolling less than 5? Okay, well, less than 5 is 4, 3, 2, 1. Right, we didn't say equal to 5, we said less than 5. There are 4 options there out of 6 total, which again reduces to, in this case, 2/3. Or 2/3 is 0.67, or about 67%. About 2/3 of the time, we'll roll less than a 5. The probability of rolling less than a 10, well, they're all less than 10. That one's guaranteed, right? That would be a 100% probability. It doesn't matter how many times you roll the die, it's always going to be less than 10. Okay. Simple calculations you should somewhat understand and feel okay about, right? It's this type of probability is relatively intuitive and easy to understand. Okay? And that's kind of where we're going to focus, right? So let's say each weekend you and your friend, you're going to randomly choose a movie from the movie collection that you have. You have 45 action movies, 31 comedies, 12 documentaries, and 3 musicals. Okay, what's the probability that you would choose a comedy? Hey, well, there are 31 comedy movies. Okay, and if you want to find the total possibilities, we would add all these up: 45, 31, 12, and 3. So there are, and I just happen to know this previously, there are 91 movies to choose from. So 31 divided by 91 will give you 0.341, or about 34.1%. So about a third of the time, which makes sense. Maybe you do the same thing for a musical. Right now, there are only 3 musicals out of all 91 movies. And 3 divided by 91, 0.033, we'll call it. Or about 3.3% of the time. There are a lot less musicals. They're going to be randomly chosen a lot less frequently. Okay, so it's much more likely for us to choose a comedy than it is to choose a musical. If we're just going to randomly pick a movie from the collection. think about this example because it's easy to understand. It's something that you could actually do, right? If you had a friend with a bunch of movies and everything wasn't all streaming now, you could go randomly choose a movie from a collection, right? And it intuitively makes sense. And the reason that I'm focusing on it some is because we're going to mention this example again in a few minutes in a slightly different context. Okay? And I just want you to think about essentially how often you would choose a musical, right? If that would feel like it would be unusual, or if it wouldn't happen all that often. In probability, something can either occur or it doesn't occur. Right? So you flip a coin and either you get heads or you don't get heads, right? You roll a die and either you get, an odd number or you don't get an odd number. Okay, so if we know the probability of one thing happening, we can figure out the probability of it not happening. Okay, and we call that the complement, okay, or the complementary probability, the complementary event. Okay, it's the probability of the event that not occurring. Okay, so for example, if we just go back real quick, there's a 34.1% chance that we choose a comedy. But if we subtract that from 100, I'm not sure I could do that in my head quickly. Let's see. 100 minus 34.1, 65.9. 65.9% chance that you don't pick a comedy, right? That you choose one of the other movies. And that should kind of, that should make sense, right? And so this is the probability of choosing one of the other movies, but it's also the probability of not choosing a comedy. Okay, so again, here, if we wanted to choose movies, what's the probability that we would not choose a documentary? Well, we can calculate all of the other things that are not documentaries, add them all up and divide by 91. Okay, but we can also calculate the probability of choosing a documentary, which was 12 out of 91. 0.132, or 13.2%. And then we could say, well, if this is the probability of choosing a documentary, then the probability of not choosing a documentary is just 1 minus 0.132, which is 0.868. The exact same thing you got here. And so it doesn't matter which way you calculate that probability, because it's the opposite probability, you're going to get the same answer both ways. Okay. But the important thing to remember is that is the probability of the event not occurring. Okay, so here, out of 800 large purchases made at a computer retailer, 336 were desktops, 398 were laptops, and 66 were printers. We are going to randomly choose as part of an audit, one purchase record chosen at random. What's the probability that it's not a laptop? And so we're going to randomly choose one of these purchases, and we want to know what's the probability that it's not a laptop. Well, there's a couple of ways that we can do it. Okay, let's start with the way we just learned, right? So the probability of choosing a laptop, there are 398 that are laptops out of 800. I don't know that exactly, but it's going to be really close to 0.5. 0.4975. Or 49.75% chance that you choose a laptop. Okay, the probability of not choosing a laptop, well, that's just going to be 1 minus 0.4975. That I can kind of do in my head. That's going to be 0.05125 or 5025. Or 50.25%. And so this is the probability that you don't choose a laptop. which you can also calculate by adding up 336 plus 66, the two other objects, right, the printers and the desktops, and dividing by 800, which should give you the same result. 336 plus 66 is 402 divided by 800, 0.5025, or 50.25%. So up to this point in the examples that we've talked about, we focused on one particular type of probability. And these have somewhat different names depending on the textbook that you see. I believe we would refer to this as theoretical probability. But the idea being that there are other types of probability as well, other ways that we can calculate probabilities, some of which you might be familiar with even if you don't really realize it. And so we're going to talk about the two different types and how they relate to one another briefly. And then in the next section, we're going to talk a little bit more about how to calculate some probabilities. Probability, or what we call theoretical probability in this textbook, or in some cases, I've seen it called classical probability. It assumes that every outcome for some particular event is known. And so, for example, if you flip a coin, you know you're going to get either heads or tails. If you roll a die, you know you're going to get 1 through 6. Okay, if you pick a card from a deck, you're going to get one of the 52 cards from the deck. Okay, you know all of the different possible outcomes before you do it. Okay, the same is true for something like a lottery number. Right, now, you would not want to sit and write down all of the possible combinations of numbers that you could have for a lottery. But if you had time and energy and somebody paid you to do it, you probably could. Okay, and then from that, you could calculate the probability of randomly choosing one, okay, and getting it right. Okay. In all of these cases, we know all of the possible outcomes, right? We know all of the possible lottery numbers, even if we wouldn't want to write them all down. We know all the possible cards in a deck, or all the possible outcomes of rolling a die. Okay, and so from that, we can calculate probabilities before we ever do anything, right? We can determine the probability before the event because we know everything that can happen. And we know everything that can have an effect on that event, okay, or all the possible outcomes of that event. And so this just means that we can calculate things by just asking a question, essentially, without having to consider any actual data observations. Okay? But there's a different type of probability that we can use, and we can use it based on collecting data. So now let's observe an event a whole bunch of times and see what happens. Okay? And then if we observe that event a whole bunch of times, maybe we can then predict what might happen later based on what we observed. Right? So empirical probability is based on actual experience or observations, data measurements. Right? You have to actually measure something first before you can then predict or use a probability to predict something about it. Okay? Remember, it relies on measurements of the same or similar events, right? Previous events. Okay? So for example, sports statistics are great examples of empirical probability because of the way that we discuss them, right? So a baseball player hitting a home run. If a baseball player, hits a home run 1 out of every 10 at bats, right? So 10% of the time. Right? Well, then you might say 10% of the time you could expect him to hit a home run, right? Maybe it's, it's not always going to exactly land that way. Yeah, but maybe it kind of averages to that over time, You would, in order to make that prediction, you have to let the baseball player hit the home runs first. You got to count how many he hits and how many he doesn't. Now, the same is true for when they predict rates for defaulting on loans, right? Or for successful medical treatments. You have to test the treatment first before you can figure out if it's successful, right? And then you can use, you know, the number of cases where it was successful to predict how often it would be successful. And same thing is true for, like I said, with a loan. You have to wait for people to default on the loan or default on their loans, and then, you know, figure out how many defaulted on the loans of, you know, and get a percentage. And then you could say, well, it seems, you know, we might expect 12.5% of people to, you know, default on their loans or something like that. All of these probabilities are based on observing the same event over and over again. Okay. Another good one, that's another good example is, because the NFL is almost at the Super Bowl, is the completion percentages, right? Where a quarterback throws a pass, right? And so the receiver can either catch it or he doesn't, right? If he catches it, you know, 70% of the time, then, you know, the accuracy or the, you know, percentage of received passes is 70%. Well, you could say, in a way, using empirical probability, you could predict that 70% of the time you might expect the quarterback's pass to be caught, right? And you would think about, you may not think about it exactly that way, but that's what you're doing when you look at those statistics. You're saying, well, if he's done 70% up to now, well, then that's probably what you should expect in the future. And so empirical probability is entirely based on observing events that you can't predict the outcomes. We can't predict if the guy's going to catch the ball every time. We have to throw the ball and let him catch it to see if he's going to. Right? And so that's where empirical probability differs from theoretical. Right? We don't have to do anything to calculate a theoretical probability. Right? We have to do things. We have to observe events. Okay. Now, for things like coin flips or you know, rolling a die, right? If you were to flip a coin 50 times, 70 times, 100 times, or roll a die 50 times, 100 times, as you do that, you'll notice that you don't get, you know, the exact probabilities each time. Okay. You know, if you flip a coin 50 times, you might get, you know, 48 heads and 52 tails, or if you do it 100 times. That's not exactly 50-50, but if you keep going and keep going and keep going, right, it'll work its way out to be pretty much 50-50. Okay, and that's what's called the law of large numbers. Right, the more times that you run a probability experiment, the closer and closer your empirical probability, the measured probability that you got from the data, okay, by measuring the event over and over again, will approach what you would theoretically expect. Okay, and so if you roll a die over and over and over again, you expect about 17% of the time to get each number. If you keep doing it, right, eventually you'll find that about 17% of them will fall into each number. Then it might take a while, depending on, you know, how you roll and things like that, but it'll get there. So Mark rolled a fair die 500 times. He got the following results that you see here. We want to compute the theoretical probability of rolling an even number. Remember, for theoretical probability, rolling an even number, 2, 4, and 6, that is going to be 3 out of 6, or 1/2. So again, 50% of the time you would roll an even number theoretically. Now from his results, let's compute the experimental or the empirical probability of rolling an even number. Okay, and so here he rolled 500 times, so that's our total. Okay, he rolled a 2 78 times, and then 4 and 6 77 times. 78 plus 77 plus 77. 232 out of 500, which is less than half, but you know, not much less. 4 point. 0.464 or 46.4% compared to 50%. So in this case, you can see that the law of large numbers, but essentially implies that if we keep doing this over and over again, this 46.4% is going to approach that 50%. And I would argue if you rolled, well, I mean, I'm going to know the answer to this question, but if you rolled a die 500 times, what's the difference between 50% and 46%? Not that much, right? The difference is really, it's 18 rolls out of 500. So if you keep going and keep going, that 18 will clear its way out, and this will approach 50 before you're finished. You did 1,000 or 10,000 or 100,000, which would be ridiculous, but it would work out to be about 50% each time for even numbers and odd numbers. Now, coming back to what we talked about well at the beginning, I just wanted to point out one thing, okay? I told you to think about the randomly choosing a musical, right? And how, whether that would feel unusual, okay? In statistics, right, we generally define rare or unusual events as things that happen less than 5% of the time. And now, that can change. That's a really flexible definition, if you will, depending on what type of research and things that you're doing. It can be 1%, can be 0.1%. Okay, but it's the designation that becomes important. We're going to say that choosing a musical, that would be rare, right? And it should feel like a rare event. And that's what I was trying to imply before. It should feel unusual, right? If you were just randomly choosing movies, I mean, if it would take you 3 out of 100 times, you would choose a musical, right? So it would take you 100 different, if you did it once a week, 100 different weeks to watch those 3 musicals that they have. I mean, that would be rare, right? It would feel rare. And so that's what I want you guys to understand, okay, here. We're going to use this definition for rare events, right, for something else as we go forward. Okay, but this is how it should make sense to you how this is a rare event, right? If something less than 5% of the time, probably, you know, if you get 100 movies to choose from, it's probably not going to happen all that often, right? It's going to feel unusual when you choose that musical, right? And so I wanted to point this out here. And like I said, we will revisit that 5% much over the next few weeks. So in a college of 5,000 students, 150 of them are math majors, right? We're going to randomly choose a person. Would it be unusual to randomly choose a math major, right? There are 150 math majors out of 5,000 students. And if we're just going to randomly pick one, I'm not sure what 150 divided by 5,000, 0.03 or 3%. So yeah, like the movie, this would be unusual, right? 3 times out of, you know, you have to choose 100 students to get 3 that are math majors in this case. It would be unusual if you just randomly chose one and it would be the first person. And so think about how unusual things, you know, rare events would happen less than 5% of the time. Okay, and hold on to that thought as we go forward in later chapters and in later sections. In the next section, we're going to talk about a really common mistake in statistics, and I'm going to show you guys a few different types of visualizations, some other important things, some other ways to discuss some new information. If you got any questions, please let me know.